Dear students, today we will try to understand Maxwell-Boltzmann Statistics. First of all, we will consider a system which contains capital N distinguishable particles. Those N distinguishable particles, they occupy energy levels with E0, E1, E2, E3, E4. You can imagine, suppose these are energy levels. This is E0, E1, E2, E3 and E4. In all, they contain total number of distinguishable particles, that is capital N. Now suppose N1, small n1 is the number of particles that are present in the first excited state. This will be the zero energy ground state. This will be the first excited state. Suppose N1 particles are present in this energy level. Similarly, suppose small n2 particles are present in second excited state and n3 in the third excited state, and so on. This type of pattern, this is simply known as the thermodynamic probability, which is represented by W. You have gone through this term in the previous classes. So this basically gives the thermodynamic probability of a given macro state. In a macro state, there can be number of microstates. I have also given you an example regarding this in the previous lecture. So in general, this number or this number of particles is basically a very large number. So to determine W, that means the thermodynamic probability, or that means to determine how many microstates correspond to a macro state, it is simply given by this expression. W is equal to capital Ni, total number of particles, factorial. This is the small n1, number of particles in the first excited state, number of particles in the second excited state, number of particles in the third excited state, and similarly to nj excited state. So you can see here they are all in multiplication. So we can write this by a simple symbol pi. This means multiplication, n1 multiplied by n2 factorial multiplied by n3. You can simply write it as pi. I runs from 1 to n, ni factorial. So this can be a representation. As such, you can write, suppose n1 plus n2 plus n3 plus n4. You write this as a summation. Similarly, for this multiplication, you write it as a pi symbol. You have to remember this. This is for multiplication of product, and summation is simply for addition. Okay. And one more thing you have to remember here, this n is basically the total number of particles, that means summation of small ni particles. Okay. Now, it is possible to realize a given energy level in more than one way. That means a particular energy level can have, suppose, 3 particles of one type, and in the next 3 more particles of second type, and so on. That means there can be more than one quantum state, but they will be having the same energy. When this happens, this is simply called as degenerate or degeneracy. That means the energy levels, they have the same energy, different energy levels. If they have the same energy, they will be simply called as degenerate. Now suppose we represent this degeneracy by a symbol small g subscript I, gi. Okay, or this is also sometimes called as multiplicity of the energy level. Suppose we are dealing with the energy level ei. Okay, that means the different energy levels having the same energy, those will be degenerate. So those are simply represented as gi. Now how to calculate this? Suppose we will take a simple example here. Suppose there are two particles in the ith energy level. Suppose there are different energy levels. The ith level contains two particles. So now you have to find it is degeneracy. Degeneracy will be simply gi, that means the degeneracy of the ith state, and how many particles? 2, and you will square it. That means gi square. So this will be the possible distribution. Similarly, if you have now ni particles in the ith energy level, then the degeneracy will be, or possible distribution will be, simply gi superscript ni. So very simple here, you have to remember. Now you can calculate for 3 particles, 4 particles, 5 particles, and so on. So the thermodynamic probability for the system of n particles can be given by taking into consideration the degeneracy. Also we can write this as W, that means the thermodynamic probability, will be equal to Ni. Now pi I, it is simply the product. This will be product. We have to introduce the degeneracy term also. We will write it as Gi superscript Ni upon Ni factorial into constant. This is the very important relation you have to remember for thermodynamic probability involving degeneracy also. This is the very important relation here. So, but from the previous classes or from the previous semester, you know that the entropy, which is represented by capital S, and the probability W of a given state of a system can be related to Boltzmann equation, which is S is equal to K ln W. This is the simple relation, well known Boltzmann equation in the statistics. Okay. So the probability must be a maximum. You have to remember, for equilibrium state, the probability should be maximum. That means the probability must be a maximum for an equilibrium state. So if we take equilibrium conditions, then this W should be maximum. We can write this Boltzmann equation by only making this part here S is equal to K ln W maximum. That means now the probability is maximum. When the probability is maximum, that means it is at equilibrium state. Okay, this is equation number, suppose 4. Okay. Basically, why we have taken this equilibrium state? We are interested in finding a distribution that will make W, that means the thermodynamic probability, maximum. Now we can take this relation into more convenient form here. If you want to take a maximum of a quantity, you know that its first differential is basically equal to 0, or it will vanish. I have written here that it is more convenient, however, to maximize logarithm of this thermodynamic probability. We know from calculus, that means from differentiation and integration, that at maximum, for maxima and minima, the first derivative is basically equal to d by dx is basically equal to 0, or that basically vanishes. So we will take into consideration this uh, property, and we will write it is first differential or change in. We will take logarithm of first ln w, and it is differential. It should be equal to, this should be equal to 0 for a maximum quantity. That means it should be equal to 0. But we know from partial differentiation we can solve it. That means we can take the partial derivative of ln of w upon n1 and dn1 plus d ln w upon dn2 into dn2 plus d dou ln w upon dou n3 into dou n3 plus so on up to ni. Or we can simply write it as summation I dou ln w upon dou ni d ni will be equal to 0. It is basically the complete partial differentiation of this term. You can go to the mathematics for chemists and you will see it is very easily given there. So now if we confine our investigation to a closed system, why now we are taking a closed system, not an open system in which the number of particles remains constant, total number of particles, because if it is a closed system, the number of particles cannot change. Okay, that means closed system, and those are independent particles, very important here. So first it should meet the following requirements, what we know for a closed system here. So the total number of particles is constant, because if it is a closed system, what may be the number of particles there, they will remain constant. They cannot be exchanged with the surroundings, nor from the surroundings any particle can enter into the system. So the total number of particles, that means summation ni, will be simply constant. You have to remember this summation of small ni, that means n1 plus n2 plus n3 plus up to n, they will totally form the total number of particles of the system, that is basically constant. Also the total energy we represent here with capital U of the system is also constant, which is basically equal to ni ei. This is also constant, because if it is a closed system, its energy will also be constant. So we know the differential of a constant is basically equal to 0 if we take the constancy of total number of particles. That means we will take differentiate this to this n, which is basically a constant. So it is differential will be equal to summation d will be simply equal to 0. And similarly for this du will also be equal to 0. So here you will see it, that basically this change in total energy, because if total energy of a system is constant, which is change will be simply equal to 0, or the first differential will be equal to 0. Summation ei dni will be equal to 0. Now we will take the equation second, and we will take logarithm on both sides. The last equation, okay. So we will write it here, ln of w is equal to ln of n factorial. You know log m into n, you can take it as ln of, if it is a log m here, ln of m into n, suppose you can make it to ln of m plus ln of n. Similarly, we have taken the equation second and taken the log to both sides. Okay, so we have written it as ln of n factorial plus summation ni ln gi. Okay, but it is divided by ln ni. So if it is divided, it will be now in the, if you take it to the numerator, it will be minus summation, but with the logarithm function here, ln of ni factorial. ln of some constant will be also constant, so it constant will remain. We are actually taking this equation into consideration. You will see here equation number second. It is very simple. This is equation number second here. This is equation second. What we are doing, we are just taking ln of this much, ln of n factorial, because it will be m into n. Now whole term, it will be ln of n plus ln of this much, and this is in divide, it will be then negative, plus this is also multiplication, this will be also in the plus ln of constant, okay, or constant simply. So we have taken this equation and done the following. Okay, now we also know Stirling approximation, which is if this x is suppose very large, you know ln of x factorial can be written as x ln of x minus x. This is simply the simple approximation of Stirling approximation. Okay, Stirling approximation. We will apply it first for this ln of ni here, and similarly we will also apply it for ln of ni factorial. So this equation 10 can then becomes, if we apply this approximation here, first we will apply it for ln of small ni factorial. It will be ni ln of ni factorial here, this part ni ln of ni factorial. It should have been minus, but it is basically minus term. Minus minus will be plus here, so that is why it is plus summation I ni plus constant is there. So we have solved this part by simply by Stirling approximation. Similarly, this can also be written in this form by following Stirling approximation. That means n ln n minus n, then the rest term will be the same, plus summation I ni ln gi minus, you know, summation of ni particles, it becomes basically the total number of particles, which is basically represented by capital N. So this capital N and this is negative, these two terms will go and you will get this term. Okay, so we got this one, equation 2. Simply what you have to use Stirling approximation for equation 10, for first for ln ni factorial and then for ln capital Ni factorial, and you will get this equation. Now we will differentiate this equation 12, but we are giving here conditions that this total number, if it is a closed system, obviously the total number of molecules or total number of particles will be constant, and it is degeneracy, gi is also constant. So we are taking 2 points into consideration for a closed system, n and gi are constant. Now if you look into this equation here, equation 12, and first we will differentiate it. This will be simply d ln of w. Now n, this is constant, we have taken here n ln of n, this becomes a constant, whole term becomes like a differentiation of constant will be 0, so this will go. But this one, this turns out to be the uv differential of the uv form. That means first you have to differentiate first function, take out this, and differentiate second function. Similarly you will get these, and if you get ln of gi and differential of gi, that will also be equal to 0 because gi is a constant also. Then ultimately you will get these three terms. That means summation ln gi dni minus summation ln ni dni minus summation ni d lni. We have done nothing, we have used uv functions here and differentiated those, and we also took into consideration that the total number of particles and gi is constant. If you get a term like differentiation of gi or differentiation of ln gi, that will be equal to 0, or differentiation of n, that will also be equal to 0. So you will get these two terms. Okay. So, but here we will further simplify this equation number 13 here. If you take this summation ni d ln ni, you know it is basically equal to this d ln ni can also be represented as this term here, ni d ni upon ni. Okay, this ni and ni will go, it turns out to be summation of differentiation of small ni particles. But if you take the summation, this becomes n, but that is also constant, so that is why it becomes equal to 0. So this term also becomes equal to 0. So from this equation, what we got from equation 14, that at equilibrium the differential of this ln w is basically equal to summation of ln gi dni, this term, minus summation I ln I dni, which will be equal to 0, because this term will be equal to 0 when you have to maximize this. Okay. Now this equation 15, it is very important relation here. Equation 15, this basically gives the change in, because it is differential, that means change in ln of w, which result is when the number of particles in each energy level is varied, dni change, which in each energy level is basically varied. Okay. Now this was the case of closed system up to here, but if we take a system which is open now, then the number of particles, that means the ni, would vary without restriction, and the variation would be independent of one another. It would then be possible to solve equation 15 by setting each of coefficients of dni terms in equation 15 equal to 0. So then all terms here, they will be ultimately become dni terms will be equal to 0. But we are not taking the open system, we are taking a closed one. N is constant for closed systems. The values of dni are not independent of one another here. Why? If you see the equation number 14, there is change with respect to small ni particles, so those are independent of one another. Again, the energy of the system is constant. At the start, we take 2 points into consideration, that energy is also constant. So 2. Then solve equation 15 subject to the constraints of equation 6 and 7. Then we have to take equation 6 and 7 into consideration, putting these constraints. So the desired solution is basically obtained by a method that is called as Lagrange's undetermined multipliers. We will discuss this method in the upcoming lecture, but here you have to remember here simply that this equation 15 can be simply solved by Lagrange's undetermined multipliers. So we will write equation 15 in this form also, because that is log m minus log n, that will be equal to log m by n. So we will write it as summation I ln of gi ni dni, which is equal to 0. Now from this method, Lagrange's undetermined multipliers, it is basically we have to actually multiply some arbitrary constants. Now what we do here, We are multiplying equation 8 and 9 by arbitrary constant, suppose alpha and beta. Those are known as Lagrange's undetermined multipliers, and subtracting from equation 16, and we will subtract that from equation 16 also. So we will get in overall this type of equation. Simply what you have to do, you have to multiply equation 8 and 9 by arbitrary constants alpha and beta, and then subtract it from this equation. You will get this summation I ln of gi ni minus alpha minus beta ei dni is equal to 0. Okay, here we can now select the value of alpha or beta. We have to take the value of alpha and beta in such a way that one of the terms here, one of the terms in summation, this is the summation part, becomes equal to 0, and this dni, it is independent of this because this cannot be 0, so it is immaterial because number of particles cannot be 0. If the number of particles will be equal to 0, then we have considered a nothing system. So the remaining dni terms then become independent of one another, since dni can be obtained from these dni terms. If you see the equation 8, dni terms are there. Okay, so if dni is immaterial, we will take that out. We will take only the coefficient of dni. The coefficient here, I will show you the equation again. Equation 17, here this will be the coefficient of dni. Here, these are dni terms. This will be the coefficient, this much. That means this coefficient will be equal to 0. We have to make this coefficient equal to 0. Here we will write it as only the coefficient ln of gi upon ni minus alpha minus beta ei will be equal to 0. Or you can simply write it as ln of gi, take these two terms to this side, they will be plus alpha plus beta ei. Or you can also write it as ln of ni, taking this term to also, it will be ln of gi minus ln of ni. So you can see that you will get this equation, then ln ni is equal to ln gi. We have done nothing, we have simply taken log of m upon log n, which will be equal to log of gi minus ln of ni. Okay, ln of, that means minus ln of ni will be equal to minus gi, minus and minus will go, but for these two terms minus will be multiplied. Okay, or we can simply write it as, we can multiply it by exponential, and this will go, exponential this will go, and for this exponential will remain. So ln and exponential, it will turn out to be this equation. That means ni will be equal to gi e superscript minus alpha minus beta ei. This equation, it is a very important relation. It is basically one of the form of Boltzmann distribution law. Yeah, it's basically one of the form of Boltzmann distribution. This basically gives the most probable distribution. Most probable distribution for a microstate. That means which microstate has maximum number of, which macrostate has maximum number of microstates. That will be the most probable distribution for a macrostate. That, or you can in other terms say that it gives basically the occupation numbers of the molecular energy levels for the most probable distribution in terms of energies ei, the degeneracy gi, and the undetermined multipliers alpha and beta. What is most probable distribution? Suppose we have a distribution like this. One is there. Suppose this is one macro state, this is one macro state, this is another macro state, and this is also another macro state, MAC. Okay, now to remember, this is another. And these macro states, they basically contain micro states, and this is the sharp one. This contains the maximum number of micro states. So the one which contains the maximum number of micro states, that will be simply the most probable distribution. Okay. Okay, thank you.